All right, period five friends. Right at the end of the period yesterday, we were taking a look at this graph that we made, dragging the big set of blocks and masses on the table, and a couple of important things to note here. Um, oh gosh, there's a period of time where I'm applying a force, but the velocity is zero. Okay, so this thing is at rest during this window of time where I'm applying a variable amount of tension. And so the understanding that we got to yesterday was the that the friction force was varying in response to the tension force in order to balance it out and keep the object from going into motion. So for objects with velocity of zero, objects at rest relative to the surface, the frictional force varies. And so that's called static friction. It's represented as FFS, okay? And it's a variable amount up to this threshold value here, okay? So there's an equation that says FFS max, the maximum amount of static frictional force, that's equal to something called the, oh gosh, how do I want to term this? Well, the equation for it, I'm going to take it times mu S times the smoosh push force. Okay, so this kind of agrees with our findings from the other day that the friction is going to depend on surface type and also on smoosh push. Okay, so in the equation, that's represented by these two things, smoosh push, and then mu S, which is a specific number for a combination of surfaces. If you can think about it differently, it's kind of a ratio of how much friction there is to how much smoosh push you have. Okay, so for example, you might have a mu S, you might have a coefficient of 0.5, and that's just telling you that whatever your smoosh push is, let's say you had a smoosh push of 20 newtons, then your FFS would be 10 newtons, right? Because that's how math works. So a coefficient of 0.5, your friction is going to be 50%, your maximum friction, 50% of your smoosh push, okay? And in order to know what that coefficient is, you would either try to determine it experimentally, or for over here in Canvas for today, down, boop, I included a table of values here. So mu S for wood on wood, okay? And that's what we were looking at with the setup the other day, somewhere in the ballpark of 0.25 to 0.5, okay? Then when we get over past well, I guess I should say this. So this is FFS max. You'll commonly see this written as FFS is less than or equal to mu S times FSP. Okay, and that's because, again, this is a variable amount of friction. You'll use the force addition diagram, the HBD, LARD, or CAT, in order to figure out how much friction you need to keep this thing from going into motion. You can calculate it this way. FFS is less than or equal to mu S times FSP. Then when you get over into this part of the graph, now if we look down at the velocity versus time graph, now it does have a velocity. So now it is in motion. Velocity is non-zero. And you see that the amount of friction, or at least the amount of tension required to keep it in motion, is less than this threshold value, okay? That's because once it's in motion, it's subject to less frictional force than this maximum amount of static frictional force. The equation for determining that is FFK equals mu k times smoosh poosh, okay? Or said differently, the coefficient of kinetic friction, mu k, is simply the ratio of kinetic friction to smoosh poosh. And so it operates kind of the same way as mu s. But if you look at the chart over here for these values, the static coefficient tends to be higher than the kinetic coefficient, right? Because our maximum static friction value should be a greater percentage of the smoosh poosh than our kinetic friction value. Once this thing's in motion, you're only going to have about 57% the magnitude of the smoosh poosh as friction. Whereas before it goes into motion, you could get up to 74% of the smoosh poosh as static friction, okay? You look along at some of these things, very high coefficients. 1, rubber on dry concrete. But again, you change the surface type. You make that wet concrete. Water fills in some of the gaps in the concrete, and it's much less frictiony. Only about 30% of the smoosh poosh available for friction force. Okay. Teflon is a substance that's used to coat nonstick pans. You can see it's a very, very low coefficient. So if you had two Teflon coated surfaces that were in contact, you have a very low coefficient of static friction. And actually, you have the same value for kinetic and for static. So it's kind of unique in that respect. Where do we have? There we go. Synovial joints in humans, in addition to an excellent flavoring agent, they have very low coefficients of static and kinetic friction, so 0.01. So only about 1% of the smoosh poosh is the magnitude of the frictional force. And once the joint is in motion, you only have about 0.3% of the smoosh poosh showing up as frictional force. So that's how this table of mu values helps you establish the amount of friction. So you've got to figure out what types of materials you're dealing with, or often it's just given to you in the problem. This is the coefficient of kinetic friction. And then you've got to figure out the smoosh poosh force, and you can figure out the friction force from that. Okay? That's about it.